All right, now I am about to show you the next step where we left off right here. We found the heat energy that the water absorbed. So how do you find the specific heat capacity of the metal? Let me show you how you do that. I'm going to change colors to green. All right, now the specific heat capacity of the metal, I'll call it Cm, right? For M is for metal. How do you find that? You find it by solving the equation, this equation. The mass of the metal times specific heat capacity of the metal times the change in temperature of the metal. Does this equation look familiar? It's the same as the equation we used before for the water, except instead of W for water, I'm using M for metal. The heat that the metal, in this case the metal was hot, and then you put the metal in cold water, so the metal cooled off. So the heat that the metal lost is equal to the mass of the metal times the specific heat capacity of the metal times the change in temperature of the metal. So you have to solve this equation for this. Once you solve it for this, you will have the specific heat capacity of the metal. That's how you solve this. That's how you figure this out. So how would you do that? You would have to know how much heat that the metal lost. You would have to know the mass of the metal. You would have to know the change in temperature. The change in temperature for the metal. I won't write that. It takes too long to write that. This is an S. These are S's. Yes, these are S's. Okay. So how do you know those things? How do you know those things? Well, it happens to be the case that in this universe, in our universe, when you put something hot in something cold, you get always the same result. And that result is the hot thing will get cold and the cold thing will get hot until they are both at the same temperature. That's how this universe works. This is some law of thermodynamics of the universe. If you put something hot into something cold, the hot thing will cool off and the cold thing will warm up until they are both the same temperature. So what does that mean? That means that whatever heat the hot thing lost, well, that heat must have been gained by the cold thing and by the environment around the hot object. Now we used 2 cups here, and so that is our way of trying to make sure that the heat that the metal lost was gained only by the water. I mean, it's not perfect, but it's quite close. Right? So let's assume that all of the heat that the metal lost was gained by the water. What does that mean? Well, that means that, you see, we just calculated how much heat the water gained. It's this much heat right here. So using that law of thermodynamics, if the water gained this heat, where did it get that heat? That's right, it got that heat from the metal. So that means the heat lost by the metal is equal to the heat gained by the water. These are the same thing. Except when you gain heat, like the water gained heat, that's we call that a positive heat. When you lose heat, we call that a negative heat. So negative 4,600 joules is the heat that the metal lost. We call that negative, all right? To show that someone lost heat rather than gained heat. Now, what is the mass of the metal? I don't think I weighed the metal yet, so I'm going to go dry off that metal, dry it completely, and then I'm going to weigh it. And let's say the mass is maybe some 81.129 grams, right? 81.129 grams. That's the mass of the metal. So I will plug that in here. So this is the heat that the metal lost. 89.129 grams is the mass of the metal. Did I get that number right? No, 81.129. Sorry about that. 81.129. It's 81.129 grams. That's the mass of the metal right there. And the C of the metal is what we don't know. And what about the delta T? Delta T is T final minus T initial. It's always T final minus T initial. So let's think about this. In our experiment here, what was the T final for the metal? Not for the water, for the metal. That is right. They are the same. So that T final for the water is the same as T final for the metal. Why? Because in this universe, if you put something hot into something cold, they will both change temperature until they are both the same kind of warm temperature. That's how this universe works. If you drink cold water, that cold water is going to go into your stomach and it is going to heat up there. When do you think it will stop heating up? Also, your stomach itself will start to cool down a little bit. When do you think your stomach will stop cooling down? That's right, they will stop when both things, the cold water and your stomach, are at the same temperature. If you were dead, that temperature would be slightly less than the stomach's initial temperature and slightly more than the water's initial temperature. However, if you are alive, then your body is actively maintaining a certain temperature, and so the temperature of the stomach and of the cold water will change until they stop at room temperature, until they are both at room temperature. Well, so anyways, T final for the metal is the same as T final for the water. So I will plug that in here. So this is 34.1 degrees Celsius minus. And what is T initial for the metal? Is it the same as the cold water, 23.1 degrees Celsius? No, because the metal was never 23.1 degrees Celsius. What was the temperature of the metal at the beginning of this experiment? That's right. The temperature of the metal was 99.2 degrees Celsius. So let's plug that in here. This is 99.2 degrees Celsius. Alrighty. So now we have T final minus T initial. Now we can solve this equation. This is negative 4,600 equals 81.129. I should probably keep the J here for you. Grams times cm times, what's 34.1 minus 99.2? That's right, it is negative 65.1 degrees Celsius. How is that okay? Oh, you'll see. So what do I do to solve for cm? Yes, that's right. To solve for cm, I must divide both sides by this number and divide both sides by this number. So let's do that. I guess I'll need another piece of paper. Okay. All right, so I have my fresh paper here, and I'm going to do 4,600 joules divided by this number right here, 81.129. Whoops. Yes, divided by 81.129 grams, and also this number here, also divided by negative 65.1 degrees Celsius. That equals cm times, what did I have here before? I had something before the cm. I had 81.129 grams times cm times, what did I have here? Oh yes, negative 65.1 degrees Celsius. All right. So I'm dividing both sides by 81.129 grams, and I'm also dividing both sides by negative 65.1 degrees Celsius. It's right here, and it's right here. This one is right here, and it's right there. Okay, so these cancel, these cancel, these cancel, these cancel. So on this side, I just have cm, and that equals, do it on the calculator over here, 4,600. Do you want me to put the negative? I usually just do that separately, but I'll do it for you. 4,600 divided by 81.129 divided by negative 65.1. Notice that I have used the divide sign twice. This is how we do things in chemistry. It's just a shortcut. I suggest you get used to it because it's quite useful. It makes you do less errors on your calculator than otherwise. So the answer here is 0.871. I say 0.871 because remember I'm using 3 significant figures there. 3 significant figures. 0.871 is the answer. Now what are the units? Joules over grams over degrees Celsius. Joules over grams over degrees Celsius. That's the answer. This is the specific heat capacity of the metal. What metal? That metal. It is 0.871. Now let's go see what kind of metal that was then. So I say that because this is the whole reason why we use specific heat capacity. I mean, this is one reason why we use specific heat capacity. You can often use specific heat capacity to identify a material. There are many other uses for specific heat capacity, of course. You will use specific heat capacity if you are trying to figure out what temperature something is going to rise to given some energy. So you must know the specific heat capacity of every material on a satellite if you are designing a satellite for launch. If you are designing any kind of heat-resistant material, you need to know the specific heat capacity of that. Or if you're trying to design parts for some very fancy freezer or refrigeration unit, you should know the specific heat capacity of the parts that are going to be on the inside of the unit. So this is a very useful number to know. But now let me show you how to identify a metal by specific heat capacity. So here I have some numbers, some specific heat capacities of different metals, and my metal had specific heat capacity of what was it again? I already forgot. 0.87 something was it? That's right, 0.871 joules per gram per degree Celsius. So here it is, joules per gram per degree Celsius. You see that? Let me see which metal has 0.871 or something like 0.871. I don't see one here. Perhaps it, oh look, silicon is not a metal, but it's close to 0.871. Maybe the material wasn't metal. Maybe it was silicon. Actually, yes, it appears that the closest one in here is for silicon. So if I had a material that was one of these materials, then maybe, oh, actually, aluminum is closer than silicon. Let's see, 0.92, 0.871. Yeah, that's closer than 0.71. Yeah, I think the material must have been aluminum. Now you see this is 0.92. It's not 0.871. Where does the error come from? Well, there are many sources of error. When you do this in the lab, I think that the one major source of error might be the cups. It might not be true that when you use 2 cups, all of the heat that the metal loses goes into the water. You might still be able to lose some heat through the cups, or maybe if you didn't use a very good lid, maybe some heat got lost into the air upwards. This is the most common way for heat to get lost because, of course, hot air and hot water vapor will rise. Yes. So that's one major source of error. Another major source of error is, what if you put a thermometer in here and the thermometer was touching the hot metal? Then you wouldn't be able to, I mean, it's possible that the thermometer was reading the temperature of the metal, not the metal and the water. So it's possible that if you don't stir this water and the thermometer is just touching the metal, you might not know if the metal is at the same temperature of the water. You might think that it is, but maybe it's not, and that introduces error in your calculation. So what I mean by that is perhaps the 34.1 degrees Celsius really wasn't supposed to be 34.1. Those are the, I think those are the most obvious errors in this kind of experiment. And that's all I have to say, except for one thing. This type of experiment is called calorimetry. When you figure out how much heat some object is giving off or absorbing, you use calorimetry to do that, and then you can use that information to calculate the specific heat capacity of that object. This is called calorimetry because this double cup tool here, both of these cups along with their lid, this is a tool called a calorimeter. This is just a school calorimeter. This is calorimeter. It is nothing fancy, but when people try to figure out how much energy is in a food, I mean how many calories are in food, they use a calorimeter, but it's not like this. It is called the bomb calorimeter, and it is very thick. It's not just 2 cups. It's very thick, made of metal, because they will explode something inside. Let's say they wanted to know how much energy is in peanuts. They will burn the peanuts or explode the peanuts inside the bomb calorimeter using pure oxygen gas. And then they might have water surrounding the explosion chamber, or they might just have very thick metal to absorb all of the heat. I'm not sure. I've never actually used a bomb calorimeter, so I'm not sure if they are using water there or just a very, very thick piece of metal. But although the details of the experiment are different, it is the same kind of calculation as that we're doing here. You calculate how much heat energy the water absorbed or the container absorbed, and then you use that to find the heat energy, and then you use that to find whatever else you want. In our case, we wanted the specific heat capacity. Thank you.